y value when you plug in the x value.
Awesome. Okay, so we have to have a general limit, and when we plug it in, it has to be the same. So for this one, I've got two different limits from the left and the right. If I plug in x equals 1, then I get this for the left and this one for the right. So when I set them equal to each other, I've got c equals 7. So that's the only value that will make this continuous. If I wanted to figure out if I am differentiable when x is 1, what else would I have to do?
You have to derive the two functions and plug in the x value.
Okay.
And see if they are equal.
Awesome. So I've got to see if the limit from the left of the derivative is equal to the limit from the right. For this one, will they be equal?
No.
Okay, you're right, they won't be. What will the top one become if I take the derivative?
21x squared.
Okay, 21x squared, and what's the bottom one going to become?
One.
1, perfect. So that was, if I have a to the x, I get a to the x ln a. Ln of 1 is 0, so that term cancels. And then if I derive ln x, I get 1 over x, plug in 1, and you've got 1. So this is this differentiable or not differentiable?
Not differentiable.
Not differentiable, awesome. Okay. Still waiting on Sabasa, so I'm going to do a couple more of these. Let me go up to the questions. Okay. I'm looking for... Oh, there's Sabasa. Okay, let me see if I can pull him in really quick. Okay. To calculus, maybe. Okay, that should get him in here. Okay. Subasa, can you hear me? Not quite yet. Okay, he's still working on that. So while I'm waiting on him, I want to know which of these could be a slope field for the differential equation y squared minus x squared. So if I have y squared minus x squared, what are some of the features that you would look for?
When is the slope equal to 0?
Okay. when will the slope be equal to 0 for y squared minus x squared?
When the x value and y value are the same.
Okay. Is that true for a?
Yes.
Okay, that is true for a. Is that true for any of the others?
B.
Okay, that is true for b as well. What about c and d?
No.
Okay, that's not true for c or d. Cool. So that leaves us with just a or b. Taking a look at a and b, what's something that's different in a than b?
Think the I think one is positive, showing positive slope, and negative slope.
Okay, so one's showing positive slope, one's showing negative slope. At what point?
At when x equals 0.
Okay, when x is 0 and y is what?
Y is 1.
Okay, so at 0, 1, a is negative, b is positive. So if you plug in y is 1 and x is 0 into y squared minus x squared, would your answer be positive or negative?
Positive.
Okay, so because this one is positive, which one should be the right answer?
B.
B. Awesome. Hello, Subasa. Can you hear me?
Yo,
Awesome. Welcome to the chat.
I just kidding.
All right. So I've got the mock exam posted for everybody on WeChat. I'm going to close this one out then, and we'll start going through the topics people sent me today. So I got a request to review definitions of a derivative, so I'll do that really quick. So I have two definitions of a derivative we've talked about so far. The formal definition of a derivative is the one we're more familiar with in class, and then the limit definition I haven't done as much time on. So let me zoom in a bit and get this out of the way. Okay, so the formal definition says I've got 2 points on a line, x f of x and x plus x f of x plus delta x. If you take your change in y, so that's y2 minus y1, and divide x2 minus x1, I should get the slope. If you take the limit as your change in x approaches 0, then you'll get the slope at a single point. So those two lines will meet. The limit definition is almost the same thing. I've got 2 points, x f of x, and I'm going to call this c f of c. So if I have two separate points, and then I take the limit as the x value approaches the x value of the other point, that will also squeeze them together. So that would look like this one. F of x minus f of c over x minus c is really y2 minus y1 over x2 minus x1. So the same idea. I'm taking the limit as we approach 1 point for my limit definition. I'm taking the limit as my change in x approaches 0, which does the same thing for my formal definition. Okay, any questions on the formulas?
Wait, for the limit definition, when we have to use those.
So for the most part, these are multiple choice. So if you see a multiple choice question that's in this form, so a limit that's in this form, then because that is a derivative, we can cheat and use derivative to solve it. For both of these, if you don't recognize it, when you try to plug in delta x approaches 0 or x approaches c, you'll get 0 over 0. So you can also use L'Hospital's rule to solve these. Okay, I'm going to show you 3 examples. So I've got 3 samples here that I haven't solved yet. First one is, zoom in here a little bit more. The limit as x approaches e of x cubed minus x minus all of e cubed minus e all over x minus e. Suyan, how can I solve this?
You should derive.
Okay, if I derived, what would I derive? What's my function?
So when you derive, you get 3x squared minus 1.
Perfect. Okay, so my function, the action that I'm doing to both of these x values is x cubed minus x. So then my derivative is 3x cubed minus 1. 3x squared minus 1. And then what's my x value?
E.
E. Okay, so I could say f of my slope at e is going to be 3 times e squared minus 1. Okay, if you did not recognize that this was a derivative, you can still solve it with L'Hospital's rule. So I'm going to jump over to Subasa for that. Subasa, if I just try to plug in e right now, what happens?
Plug in e here.
Yep, so for my original limit, I'm going to start over. If you just plug in e, what happens?
The bottom going to be 0.
Okay, what about the top?
Top going to be this. It's going to be 0 2.
Okay, so both the top and bottom are 0, so that means we can use L'Hospital's rule. So that tells me the limit. Oh, okay, I can't do that way. The limit as x approaches e of the derivative of the top divided by the derivative of the bottom should be the same. Okay, so with L'Hospital's rule, if you derive the top, what happens?
E.
Okay, if you derive the top, those e's are all constants. So when you derive a constant, it becomes 0. So we don't have to worry about the e's at all. What's going to happen to the x cubed minus x?
Oh, okay. When I derive that, it's going to be 3x half 2.
Okay.
And minus.
Sorry, say again?
And minus 1.
Minus 1, perfect. What about the bottom?
Bottom is 1.
1. So if I plug in e right now, I get 3e squared minus 1, which is the same thing we got with the limit definition of a derivative. Okay, so if L'Hospital's rule is easier for you, then just use L'Hospital's rule. Oh. Okay, not recognizing his name, but that's all right. So with L'Hospital's rule, this limit would be equal to the limit of the derivative of the top divided by the derivative of the bottom. What about this one? So yeah, I'm going to jump back to you. So I've got the sine at pi 6 plus h minus 1/2 over h. We're taking the limit as h approaches 0.
So you need to find the x value.
Okay, I need to find the x value. If this is the formal definition of a derivative, what would the x value have to be?
Pi 6.
Pi 6. Okay, so I'm just going to check and make sure this works. What's the sine at pi 6?
1/2.
Perfect. Okay, so I can rewrite this as the sine at pi 6 plus h minus the sine at pi 6 over h. Okay, so now that we're in the formal definition of a derivative, what's my function, and then what's the derivative?
The function is sine x
Okay, what's the derivative?
cosine x.
Okay, the derivative is cosine, so what should our answer be?
Uh, root 3 over 2.
Perfect, root 3 over 2. All right, Savasa, last one. So I've got cosecant x minus 2 root 3 over 3 over x minus pi thirds. So this is the limit definition of a derivative. If you don't like that, you can use L'Hospital's rule. Which do you prefer?
I think limit of the first one.
Okay, so we've got limit definition. So that means my original function of x has to be what?
The cosecant x.
Okay, cosecant of x. What's the derivative?
Negative cosecant x multiplied cotangent x.
Okay, just to double check and make sure this works. If this is the limit definition of a derivative, this is x, and then pi thirds would be the value we're approaching. So I need to make sure that this 2 root 3 over 3 is the cosecant at pi thirds. What's the cosecant at pi thirds?
Wait. Cosecant. Yeah, it's right. 2, 3 over 3.
Okay, it's right. So they did rationalize, so it looks a little bit weird, but it's right. So then our last step, that means this is the formal definition, or this is the limit definition of a derivative, so we can use the derivative. So I just need to plug in pi thirds into my derivative to get my answer. So this is negative cosecant of pi thirds times cotangent at pi thirds. What is the cosecant at pi thirds?
Negative 2 root 3 over 3.
Okay, so it's positive, but we got that negative on the outside. So I think you combine those, right? So this is altogether negative 2 root 3 over 3. What's the cotangent at pi thirds?
Root 3 over 3.
Okay, hold on. Negative 2. Da? I'll get there, hang on. Okay, then we said the cotangent is going to be, what? I'm sorry.
Root 3 over 3.
Okay, so that's 1/2 divided by root 3 over 2 is 1 over root 3, or root 3 over 3. I'm going to leave this one as 1 over root 3 because things are going to cancel. So this is 1 over root 3.
Yep.
Okay, so what's going to cancel?
Root 3
Okay,
gonna be cancelled.
so root 3
So-
cancel. Okay, go for it.
The answer is minus 2 over 3.
Awesome. Okay, the other way we could have done that is L'Hospital's rule. If you used L'Hospital's rule, when you plug in pi thirds, you get 2 root 3 over 3, so the top will be 0, the bottom will be 0. When you derive cosecant, you get negative cosecant cotangent. The constant goes away, the bottom becomes 1, so that I can plug in pi thirds and get my answer. So the math ends up being exactly the same. Any questions on our definitions of derivatives?
No.
Okay, jumping into the next topic. I was also asked about linear approximations, which are also called tangent line approximations. So the idea is, for tangent line approximations, we'll take a line tangent to the curve, and just follow that line up into another x value to figure out what the y value at that tangent line would be, and then use that as an estimate. So we use this if we want an easy way to overestimate a function. So for instance, how much power do I need to be to charge my heart monitor? I really don't want to underestimate. So I might use a tangent line if I know that I'm going to be concave down. That way I know I will overestimate and I will have enough power. Okay, so here's what it looks like. So normally my formula for a tangent line, I need a point and a slope. So it would be y minus y equals m times x minus x, which is really what we have here, just in function notation. So this is the y value at the tangent line at b. If I move this f of a to the other side, would be minus the y value at a, which is where I'm getting the tangent line from, would be equal to the slope at a, which is the slope I've gotten the tangent line from, times b minus a is my x value at b minus the x value at a that we used to build the tangent line. Okay. Another way of thinking about this is it's really similar to what we did with Euler's method. So for Euler's method, we said our new y value will be equal to our previous y value plus our change in y. And then we broke that change in y down to be change in y over change in x times change in x, which became this. Our new y value is our previous y value plus change in x times slope, right? So the difference is, for tangent line approximations, our slope is constant, and for Euler's method, our slope was a differential equation, so our slope kept changing every time we moved over. So graphically, it looks like this. Euler's method is more complicated, so every time that I move one change in x over, we actually change the tangent line that we use to estimate the next point. For a tangent line approximation, we don't change at all. So I've got a single point, a single slope, and we just use that to estimate the y value. Okay, any questions on the general idea of what we're doing?
No.
Can you show me the function again?
Right. See if I can scroll up enough to get both this and the picture in. Oh, wrong way. There we go. Okay, so our function is our previous y value, which is going to be f of a, that's this point in red, plus my slope, which is f prime at a, which is the slope that I will use to build the tangent line, times my change in x, which is b minus a. So really this is this formula, only my slope is not changing like we did with Euler's method. You okay? You can think about it as using Euler's method with only one step if you want, and then the math is the same.
Okay.
Okay, I'm gonna show a problem really quick, and we'll see if that helps. This file's sent on the Skype chat already, and I'll send it again through WeChat, so you guys will have a copy of this one too. Okay, so what I'm going to do is I'm going to get a linear approximation to the function f of x equals negative x plus 2 to the 1/2 power at the point 2, negative 2. Okay, so the first thing I'm going to do is I'm going to get an equation of a tangent line. So to get an equation of a tangent line, I need a point and a slope. Since we already have a point, 2, negative 2, I just need to derive this and then plug in my x value to get the slope at the point. Okay, so if I derive our function, I'm going to multiply by 1/2, decrease the power by 1, so I get negative 1/2, and then multiply by the derivative of the inside, which is 1. So that gives me this. Then I'm going to plug in my x value to figure out what the slope at 2 is. If I plug in 2, I've got 4 raised to the negative 1/2. If I have a negative exponent, I can move that to the bottom of a fraction. So this is really negative 1/2 times 1 over square root 4. The square root 4 is 2, so this is negative 1/2 times 1/2, which is negative 1/4. Okay, any questions on how we got the slope?
No.
No.
Okay, so now I've got a point and a slope. So if I wanted to make an equation of a line of it, I could use point-slope form here. So that's y minus negative 2 is equal to my slope times x minus 2. Okay, now that I've got an equation of a line, I could just plug in the x value I want. I want to figure out what the approximation would be at... Alright, I'm going to change the question to match my work. But I'm going to figure out what the value of f of 3 is. So if I plug in 3, I should get my estimate. I'm going to solve for y though, so I can be in the form for linear approximation. So just if you wanted to be able to solve for any x value, I could solve for y instead. Okay, so if I solve for y, I'm going to add negative 2 to both sides since I was subtracting negative 2 here. And I'll combine the negative 2 plus the 1/2, gives me negative... this isn't right, is it? Okay, negative 2 plus 1/2 should give me what?
Negative 3 over 2.
Negative 3 over 2. So that's negative 2 is negative 4 over 2, plus 1 over 2 is negative 3 over 2. So I've got, this is my general equation of my line. And then when I plug in 3, I'll get this. So I've got negative 3/4 minus 3/2 is the same thing as negative 3/4 minus 6/2. 6/4. 6, I can't type. 4ths, there we go. So what should my final answer be?
Minus
Negative 9.
9.
4.
9 over 4, there we go. Okay.
Wait, this is y value, right?
Right, this is a y value, and we used our tangent line to get it. So I'm going to jump back up to my graph. Graphically, what we've done is over here on the right. So I used a point and a slope to create a line, but then I used our line to estimate what the y value would be. Okay. So linear approximation, linear just means line. Approximation is an estimate. So we're estimating the value of our original function using a line. Okay. I think I'm going to wait on absolute maximum versus relative maximum for next time, and we'll take a look at some free response questions that talk about some of the stuff we just talked about. So I'm going to jump over to the 2014 free response next. We'll take a look at those together. Okay, so first one. I have grass clippings are placed in a bin where they decompose. For times 0 to 30, the amount of grass clippings remaining in the bin is modeled by our amount at that time is equal to this function, 6.687, times 0.931 raised to the t, where a of t is in pounds and t is in days. Okay, the first thing they want us to do is figure out the average rate of change of AT over the interval from 0 to 30, and then give the units of measure. So if I want the average rate of change, what are we actually looking for?
Mean value. Theorem.
Mean value theorem. Okay, you're closer. So mean value theorem says there's some point where the derivative is equal to the average slope. So I don't need all of mean value theorem. I just need one part of it. If I want average rate of change, what am I looking for?
So average value.
Not average value, because that means the average y value. What is a rate of change?
Derivative of AT.
Right, so I'm looking for the average derivative. So if I want the average derivative, what I really want is the average slope. So how can I get average slope?
Derive the function and use average value theorem.
Okay, I could. That's kind of a long way to walk around it, but let me write that out really quick, and then we'll see if there's an easier way. So you said my average a prime of t, so my average slope, would be what happens if I use average value theorem on the derivative. So that would be 1 over b minus a times the integral from a to b of my derivative, so that's a prime at t dt. Okay, is there anything you see that I could make easier?
You plug in 30 to the derivative and subtract the derivative when you plug in 0. 아닌가?
Close. I am integrating a derivative. So if I'm integrating a derivative, what's going to happen?
The normal one, the original one.
Right, I'm going to get back to the original function. So this is actually going to be a of b minus a of... I've got two a's here, but my amount at my amount at time b minus my amount at time a over time b minus time a. Which I could say, to make this a little bit simpler, my average slope is just y2 minus y1 over x2 minus x1.
Isn't it the same as value theorem?
Not quite, because mean value theorem is looking for the point where the slope is equal to your average slope between them. Let me draw out a line really quick. Okay, so let's say I've got a line like this. Okay, sure. So there's my line. Mean value theorem says if you have 2 points on this line, so points A and B, point A, point B, then there should be some point C between them where the derivative is equal to the average slope. So do this in another color. Okay, so this is the secant line. The slope of the secant line is the average slope between A and B. Which is just y2 minus y1 over x2 minus x1. Mean value theorem looks for some point C, which I'm going to mark in green, where the slope of the line that is tangent to the curve at that point, so the derivative, is equal to the slope of the secant line. which is going to look like this. So it's going to give us a parallel line. So it's very close. Mean value theorem has the average slope in it on the right side. But mean value theorem is actually solving for a point, not a slope. Does that make sense?
Yeah.
Okay. So let me mark this too. This is the tangent line. And mean value theorem guarantees that there is some point where the slope of the tangent line is the same as the slope of the secant line. Okay, so what we're looking for is just the average slope. So if I'm looking for the average slope, I'm going to use our shortcut method here. Our average slope is just y2 minus y1 over x2 minus x1. So that is my amount at time 30 minus my amount at time 0 over 30 minus 0. Okay, so this is a with calculator question, so I'm going to jump into a calculator next.
Wait, is that formula for the slope? Like average slope formula?
Right. I'll write out our general form. So my average slope okay, in function notation, average slope is equal to f of b minus f of a over b minus a. So if you're not in function notation, that's y2 minus y1 over x2 minus x1. Okay. So then I just need to get these points. So my average a prime at t is going to be equal to, I need to keep this capital since we have two a's in our problem. Okay, let me jump back into the calculator and I need to figure out what this is going to be at 30 and at 0. So let me turn this off for now. Our formula is 6.687 times 0.931 raised to the x power. And then I'm going from 0 to 30, so I'm going to change my window to go from 0 to 30. And we'll graph that. Okay, once this is graphed, I can hit second calculate a value and type in the values I want. So when x is 30, I've got this y value. And then when x is 0, I'll have 6.687. Okay, what's the best way to save this right now? Okay, I've got a problem because if I just store my value right now, I'm going to store 30 since it's my x value. So I'm going to quit out of this and we're going to derive instead. So I'll do, nope, we're looking for y value. I can just plug it in. So this is 6.687 times 0.931 raised to the 30 power. Gives me this, and I'm going to subtract 6.687 times 0.931 raised to the 0 power, which is 1. Okay, and I get this. Let's see if I can get both of these here. Okay, so this is negative 5.90 over 30. Should give me my average slope. So this average slope is negative 0.1968. And then I need units of measure. What should my units of measure be for this one?
pounds per day.
Perfect, pounds per day. So the reason why we are pounds per day is because we're looking at slope. So slope is going to be my y value over time. And I was given a y value, not a rate. So this is going to be pounds per day. Okay, any questions on the first one?
Then when do we have to use the average value of the functions?
So we're going to use the average value whenever they ask for the average y value. We're going to use average slope whenever they ask for the average slope or the average rate of change, or average derivative. So if it just says average value, then we need to use the average value theorem. That's 1 over b minus a times the integral from a to b of f of x.
Okay.
If they ask for the average rate of change, average slope, or average derivative, then I need to use f of b minus f of a over b minus a. If they ask you what value satisfies the mean value theorem, or at what x value is the slope of the tangent line equal to the slope of the secant line, or at what x value is the slope equal to the average slope. All of those are mean value theorem. Okay. Next one. I want to find the value of the slope at 15, and then interpret the meaning of the value in context of the problem. Okay, so I do have a graphing calculator, so finding the slope's not going to be too difficult. I'm going to hit graph, and what do I hit next?
It's calculate.
Okay, second, calculate. Which one?
Value.
If I calculate value, that's going to give me a of t. I want a prime of t. So which one of these is slope?
Is it intersects?
Intersect is where two lines cross.
You need to find the derivative.
Derivative, okay, so that's dy over dx. Change in y over change in x is slope. And then I can type in my value, so I want the slope at x equals 15. Okay, it tells me the dy over dx, that's slope at x equals 15, is this. Okay, so I'm going to copy that really quick. Okay. So there actually isn't any work for this since we have a graphing calculator available to us in the no calculator section. So I can just start typing right away. My a prime at t is equal to negative 0.1636. But then I need units and an interpretation of the meaning. So what are my units of a prime at t right now?
Pounds per day.
Right, still pounds per day. Last time I had a prime of t as an average. This time I've got a prime of t at a point, but the units are still the same. It's still our first derivative for both of these. So this is pounds per day. And then explain the meaning of the value in the context of the problem. So change this t to 15. At time equals 15, we have negative 0.1636 pounds per day. So what's happening to the glass clippings in the bin?
So this is telling the amount of grass clippings per 15 days.
So this is actually slope at a single point, so not for all 15 days, but at the exact point at the end of day 15. What's happening?
15th day.
Okay, what's happening to the amount of grass clippings?
Decreasing.
is decreasing at what rate? Decreasing.
At 0.1636.
Okay. Pounds per day. Okay. Any questions on A or B?
Could you show me the graphic calculated the process again?
Sure. First step, I've graphed my function here, so hit y equals and type in your graph. Second step, I changed the window. So hit window and change it from 0 to 30 because our problem says we're going from x equals 0 to 30. Okay, then graph it. Then hit second calculate and scroll down to derivative. So that's dy over dx. And hit enter. Okay, then we need to type in any x value you want. Right now if I use the arrow keys, I'm tracing the function, but it's hard to get the exact value you want if I do that. So I'm just going to type in 15 and hit enter. And it'll give me the derivative at 15.
Got it. Thank you.
Okay. If you can't graph it for whatever reason, you can also hit math and then scroll up to end derive.
Okay.
So I'm going to derive my function 6.687 times 0.931 raised to the x power, comma, in terms of x, comma, at the point 15. And that also gives us our answer. Okay, so derivatives, you have equation, variable, and your point. Okay, 10 minutes left, so I'm going to try to finish up this free response, I think. We want to find the time for which the amount of grass clippings left in the bin is equal to the average amount of grass clippings in the bin over the interval from 0 to 30. Okay, so first, I need to set up an equation. My time should be equal to the average amount of grass clippings. Okay, so my time t is equal to the average amount of grass clippings. How can I get an average amount?
Average value theorem.
Average value theorem. Okay, so what's that going to look like for our problem?
1 over 30 times the integral from 0 to 30
Okay.
of AT.
Okay, awesome. So this is what we need to solve for. This integral of 0 to 30 of AT times 1 over 30 is just a decimal answer, right?
Mm-hmm.
So I should be able to just integrate this directly, get my decimal answer, and then say that that's equal to hold on. The time at which the amount of grass clippings, okay. I actually want the time where the amount's equal to this. So what has to go on my left side?
AT.
Right. Okay, I want the time when this is true. So my amount at that time is equal to my average value of AT from 0 to 30. So what I'm going to do is I'm going to get the average value of AT from 0 to 30. And then once I've got that decimal, I'll just graph that line, y equals whatever that amount is. And then we'll calculate the intersect with our AT function. And that will tell us when AT is equal to that value. Okay, so if I want to plug this into the calculator, I'm going to type in 1 over 30 and then multiply by my integral. So how can I type this integral?
Math.
Okay, math.
And the ninth.
Okay, ninth option is function integrate.
Uh,
Okay, so I need my equation next, which is here. So I could retype this, but I do have my equation stored right now as y1. So if you want to plug it in, I could hit variables, y variables, function, y1. Okay, so I've plugged in all of this so I don't have to retype it. Okay, what comes next?
Yes.
Sorry, Sabasa, say that again?
X.
Okay, so I'm integrating in terms of x from what to what?
0 to 3.
Right, from 0 to 30. Okay, so don't forget your commas. I need a comma between my equation variable lower bound, upper bound. And then I'm going to close that parentheses. So this is 1 over 30 times the integral of a of t in terms of x from 0 to 30. Okay, so if I integrate this, I should get a decimal answer. I'm going to store this decimal answer. So hit store as alpha a. Now every time that I hit a, I should get that value. Okay, so I'm going to go into y equals. Just cleared out a function. I'll have to retype that. So I'm going to hit a for our y2. And then I'm going to retype our value for y1. 6.687 times 0.931 raised to the x. Okay, so my goal is to see when these two cross. Okay, so if I hit graph right now, whenever our two functions touch, they're equal. So it looks like they only touched once. How can I figure out at what point they touched?
The intersect.
Intersect. Okay, so how do I get the intersect?
Second calculate.
Second calculate.
And the 5 square down.
Okay.
Intersect. Then we both line.
Okay, first curve, second curve, guess. And that gives me my intersection point. So these two are going to be equal. Okay, I'm going to have to go back and figure out exactly what that value was, but a of t was equal to 2.75 26351. And then my x value at that point was here. I think having the calculator is stealing my focus away from the Word document. Okay, 12.414774. And then this is in days. Okay, any questions on what we did?
Nope.
No.
Okay, last one. So the last one says, when t is bigger than 30. So our function was only valid for t is from 0 to 30. So when t is bigger than that, we cannot use this at anymore. Okay, when t is bigger than 30, we have a new function L of t, which is the linear approximation to a at t equals 30. And we're told that it's a better model for the amount of grass clippings in the bin. I want to use L of t to predict the time at which there will be half a pound of grass remaining in the bin, and then show the work that leads to your answer. Okay, so I need a linear approximation, which is a tangent line. L of t is the line tangent to a at t equals 30. and we're told that that tangent line is a better model for the amount of grass clippings in the bin if you are above 30. Okay. Does everyone understand what's going on?
Yeah.
Okay, so what we're going to do is we're going to find the equation of the line tangent to A at 30, and we're going to figure out what the y value would be of that tangent line. That will give us 0.5 pounds of grass clippings remaining in the bin. Okay. So what do I need in order to write an equation of a tangent line?
You need the slope.
And the point.
Okay, point and the slopes.
Yeah, the slope.
Okay, cool. So I need my slope, which is a prime at 30. And then I'm going to need my point. I need to figure out what my value is at 30, which I did already get once before at the very beginning when we did f of b minus f of a for the first part. But I don't think I wrote down up here. I think I just skipped and wrote what the subtraction was, so I'll have to do that again. Okay, so I'm going to hit the slope at 30 first, since I've already got the graphs up. So I'm going to hit second, calculate a derivative. Okay, I'm going to move the cursor just a little bit to make sure I'm on the right function, so I am on the curve. I want the derivative at x equals 30. Okay, so there's my derivative. Is negative 0.0559762. Okay, and then my point, second, calculate a value at 30. Should give me the y value. Is 0.7829287. Okay, so now I don't have to write those numbers again. And then I want my approximation. So what's the general equation for a tangent line?
Y2 minus y1 equals slope times x2 minus x1.
Perfect. Okay, so that's my point slope form of a line. And then I'm told that the tangent line is LT, so I'm going to rewrite this in function notation. So this is, my y2 is my general y value, so that's L of t. L of t. Which is my amount of grass clippings that are still in the bin. Okay, minus my y1 is my y value at our point, which is a of 30. Is equal to my slope, which was my slope at the point, which is a prime at 30, times my general x value, which is t, minus our time that we got the point at, which is 30. Okay, any questions on how we got our equation?
Could you explain the LT part of it?
Right, so we were told that if we are bigger than 30, then instead of using a of t, we're going to use L of t, which is the y value of the tangent line.
Yes.
So if this is my general y value, I can substitute for LT. That's my y value after a of t doesn't work.
Okay.
Okay. So I've got my point for a of t and my slope for a of t when we are at 30, and I'm using that to create a line, LT. That will be a better prediction of how much grass there is if t is bigger than 30.
Right.
Okay. So I want to know, at what time will there be 0.5 pounds of grass remaining in the bin? So which one of these values has to be equal to 0.5?
LT.
LT, perfect. So I'm going to substitute for LT. Okay, 0.5.
Is it-
0.5 minus our a of 30 should be equal to a prime at 30 times t minus 30. Okay, so I want to solve for t. So if I'm going to solve for t, what do I have to do? Make this back capital A.
Plug in numbers.
Not just yet. Is there a way that I can solve this for a general form for t?
Divide both sides by 8 prime 30.
Okay. Okay, so that should give me t plus 30. Sorry, it should give me t minus 30. I haven't added both sides yet. And then I can add 30 to both sides. So I could say t is equal to all of this plus 30. Okay, any questions
Wait,
on... Oh, say again?
are we looking for t? Is it time?
Yes. I'm looking for what time we will have 0.5 pounds of grass. So I plugged in 0.5 for our y value, and now I'm solving for our time.
Okay.
Okay, so this gave us our time, and now I'm just going to plug in those values again. So this is 0.5 minus a of 30, so 0.78292787. Close parentheses, I'm going to divide by, open parentheses, all of a prime at 30. Oh, I guess I didn't need that. Negative 0.055, negative 0.055. 9762. Be careful, we can't use the subtraction sign for a negative on our graphing calculator. So I do need to use that negative sign. Okay, I'm just going to hit enter and we'll subtract, add. We'll add 30 to that. So, okay, that's 35.055. Nope, 35.054. I should round down. Okay, so this is t equals 35.05, not typing, t equals 35.0544. What are my units?
Days.
Days. Okay, so after 35.0544 days, there will be 0.5 pounds of grass clippings remaining in the bin if we use our tangent line approximation. Okay, that's about as hard as this can get. That's the hardest one I could find with tangent line approximations. Any questions on what we did?
No.
Okay. I'm going to save the rest of this for next class period, so we are 8 minutes over time already. And I'll post everything that we did today to the Skype chat. That way you've got a copy on your computers, as well as to WeChat if you want a copy on your phones. Thank you guys so much for coming. Please let me know if you have any other questions that you want me to talk about for next time.
Okay.
Right.
Okay, thank you.
Problem.
Thank you.
Good night.
Good.
Bye.